I would like to thank the organizers for giving me a chance to talk here in IMPA. Okay, my talk is based on recent joint work with Yonggen Cho and Sang-gyok Lee from Korea. Okay. I'm going to talk about the linear problem. IDTU omega of the modulus delta U equals 0 in space-time R cross Rn with initial function phi in x in Rn. So the at least formally this solution has representation like this it omega xc. Xc is a dual Fourier variable to x. Okay, my talk here is on various smoothing estimates, including dispersive estimate and Stricker's estimate and Kato type L2 local estimates. The result and techniques are more or less well known, but here my purpose here is to look at them in a unified, rather unified way with direct and explicit calculations. Okay. One of main assumption is that omega is real-valued function with respect to radial variables, the radial variables. So so that it does not include KDB or Benjamin Ono type equations. But okay, the main assumption is that omega prime is positive or positive for definiteness. But the important thing is that omega is bijective. Omega is bijective. So it includes omega to the power a. If a is equal to 1, it corresponds to the massless wave equations. And a is equal to 2, it corresponds to the usual Schrödinger equations. And if omega is square root of 1 plus rho squared, it corresponds to the Klein-Gordon equation with mass equal to 1. Or sometimes it represents it has been just recently treated as semi-relativistic equations, which was treated in a series of papers of Rayleigh and Lenzman. And this type of symbol, rho, to multiplied by multiplied by or divided by square root of 1 plus rho squared. If rho, if the symbol is the plus with plus 1/2, that model has been used by Nakanishi, Gustafsson, Nakanishi, and Tsai to treat some kind of Ginzburg-Landau model with vortices. And if we choose minus 1/2, then it appears in a model of the so-called improved bussiness equations. Okay. There are a number of types of smoothing estimates. It is related to the boundedness or mapping properties of the free propagator from initial state to the solutions to time at time t. Okay, the first type of estimate is the so-called dispersive estimate, such as L1 infinity estimate with pointwise decay in time, explicit decay in time. And the second is the so-called Striker's estimate. It's boundedness of L2 to some space-time integrability properties, functions or spaces. And the third type of Kato smoothing estimate, it is a boundedness of L2 type with gaining with some regularity and weight. And the last one is maximal estimate. Here the maximal function is the supremum with respect to t, and then L2 in x. Okay, there are a lot of mathematicians who contributed those type of estimates, and actually it is only a part of those, and I'm sorry if I missed someone. Okay. The first type of those smoothing estimates goes back to Erwin Siegel, but space-time integrability properties in this form is now all of those type of estimates is some kind of priority of Striker's. And the Kato smoothing estimate in a nonlinear problem is first done by Kato in treating in the study of KDB equations. Similarly, a similar estimate is known in linear scattering theory with potentials, known as H-smooth, the notion of H-smoothness, which is useful for proving asymptotic completeness of wave operators. Okay. The first part of my talk is on L2 type or Kato type estimates. Okay, here capital U is a free propagator, and again we assume that omega is real valued functions of rho. And omega prime is positive, definite. And we introduce some functions describing gaining regularity and describing regularity and weight. Okay, as for the regularity, we introduce psi sub A of rho. This is defined as a function of rho to the power 1/2 minus A times square root of omega prime. And A is bigger than or equal to 1/2 and less than n over 2. And then weight function omega W sub A is the modulus of the length of x to the power minus A. When A is strictly bigger than 1/2 and less than n over 2. And when A is equal to 1/2, we have to modify a little bit, and we put 1 plus here, and we lose epsilon to the power, like this. Okay, the first result is described as follows. Here, W sub A is like this, and psi will gain regularity according to this function. And we gain some regularity also in a spherical direction. This is described by square root of 1 minus Laplacian. Laplacian of theta is Laplacian unit sphere. So describing the gaining regularity along sphere. Okay, if we apply weight and this Fourier multiplier to the function to solutions, and take L2 normal over space-time, then it is equivalent to the constant C sub A to apply multiplied by L2 of initial functions. Here C sub A is 1 over a minus 1/2 and n over 2 minus a. So it blows up at 1/2 as well as n over 2. So it describes how this admissible range of A is optimal. And this equivalence means that it is bounded from both from above and below by with some possible constant. And when A is equal to 1/2, we have only upper bound estimate, and we have no extra gain of regularity along spheres. So for the Schrödinger case or some other cases, this estimate is essentially more or less well known. Okay. As for the dispersive estimate, we have to put make further assumptions. Okay. In this case, we assume that omega double prime is positive or negative definite. So it excludes the massless wave case, A is equal to 1, because in that case, omega double prime is equal to 0. And then assumptions A2 and A3 describe that the symbol omega is varying moderately, in the sense that if omega, if rho and rho prime is almost in a equivalent range, omega prime and omega double prime is equivalent. And A3 imposes that omega is stable under the differentiation. Okay. So there are examples satisfying all those assumptions. And we here introduce some additional Fourier multiplier with H. This function is this function appears as in the calculation of stationary phase method. Okay, this is a dispersive estimate. I'm sorry, this L infinity should be replaced by LR. I'm sorry, this is a mistake. And this rate of decay is the same as the Schrödinger case. And this, this is a homogeneous Bezoff space. And we lose some regularity with exponent n over r, but we somehow we compensate by means of h, and h is related to the symbol omega. Okay. in the if we describe R by the Bezoar space or homogeneous Bezoar space, the dispersive estimate is described as follows. Okay, the corollary is a Strikas type estimate. This is automatic. From those dispersive estimate, the corresponding Strikas type estimate is now the standard in non-endpoint case. This is done by, for instance, Ginevra and Bellows and duality argument, and in the endpoint case follows from the arguments of Kiel and Tau. So I omitted the details. Okay, let me describe the proof of the theorems 1, 2, and 3. Okay, the first equivalence is written as follows in the first line. Okay, for that purpose, we expand initial functions, Fourier transformed initial functions by spherical harmonics. Spherical harmonics, I mean Y, super L and sub K, and A, Lk is the corresponding coefficient. Okay, this spherical harmonics has Fourier transform on the sphere with explicit form with written with Bessel functions of first order. Here, nu is proportional to k. K represents the quantum number of, for the along the spheres. Okay, and okay, so the corresponding free waves with weight and Fourier multiplier is written explicitly like this. Here, psi sub A comes here because this bk is a Fourier transform with respect to a radial variable, and omega sub A comes here explicitly like this. Here R is the length of x, modulus of x. Okay, this A tilde has additional extra factor 1 plus k times k plus n minus 2 because spherical harmonics is the eigenfunctions of minus Laplacian on a unit sphere with eigenvalues k times k plus n minus 2. Here, this contribution corresponds to the gain of regularity along spheres. And we have rho to the power n minus 1 divided by 2. This corresponds to the integrability along radial variables measures with weight r to the power n minus 1. Okay, since spherical harmonics is form completely orthonormal system, so this claim is equivalent to say that the corresponding coefficients are summable in squared and over K and L. Okay. So we are going to prove those equivalence. Okay. Those from now on we mimic the argument of the earlier works of Koenig, Ponce, and Vega, and we start by writing explicitly the L2 norm of factor coefficient B Lk. Okay, and we make a change of variables tau equal to omega of rho, since omega is bijective, and the corresponding Jacobian comes here. And we apply Plancher's Parseval formula with respect to t and the dual variable tau. And then we perform another change of variable and come back to rho. And the corresponding Jacobian comes here. And in fact, we have chosen psi sub A to cancel the Jacobian, and the power rho to the power 1/2 minus A is okay, appears here after a simple change of variable. So we have completed separation of variables with respect to rho and S. So the problem is convergence of those integrals and corresponding summability with respect to K and L. Okay, the integral with respect to S. Okay, this integral is explicitly calculated under the help of gamma function, and when k is large, this nu is proportional to k. We apply the Starling's formula to know that this integral is equivalent to the CA multiplied by 1 plus k to the power 1/2 minus a squared. And as for the integral with respect to a tilde, we end up with this first factor came from the contribution to the from the eigenvalue of Laplacian over the unit sphere, and the rest is the repetition of the definition. And as for the factor, the power to the k exactly cancels out, and we end up with the required equivalence. So, okay, when A corresponds to 1/2, the situation is little changed, and we lose extra regularity along spheres, and okay, the corresponding summation is explicitly calculated like the resulting integral with respect to r and rho. Okay, now we here you make use of the estimate of Bessel functions, which should be uniform with respect to nu. So the constants should be independent of nu and r. So we decompose integral with respect to r in 3 regions, and the corresponding contribution is just constant multiple of divided by rho. So this power rho cancels out, and we have the required L2 summability of coefficient A, L, K. Okay, this is the outline of the proof of theorem 1. Okay, as for the theorem 2 and 3, we again describe everything more explicit and more direct, and essentially we reduce everything in one-dimensional case. In one-dimensional case, it is rather straightforward. So here I describe how to reduce the multidimensional problem into a one-dimensional problem with the help of Bessel functions. Again, okay, here the essential estimate is described as follows. Okay, this n is dyadic number, more explicit 2 to the power j, and we estimate the corresponding oscillatory integral with respect to rho in inside or near the origin and outside the origin. As is standard, near the origin, we perform the integration by parts. It is standard. And for the region outside the origin, we write the contribution of Bessel function by writing the corresponding integral with respect to theta by sum of two oscillatory integrals, because here we have oscillatory factor e to the power I t omega of n rho, and from this contribution we have e to the plus and plus minus I rho. So we have new phase functions phi plus minus rho, which is defined by t of omega of n rho plus minus r rho, which has critical points plus minus plus t n omega prime of n rho. So all you have to do is apply the so-called Fandel-Copt lemma according to, for instance, book of Elias Stein, and we finish the proof of the key lemma. And then by making dyadic decomposition with respect to phase space, we complete the proof of theorem 2 and 3, and those dispersive estimate yields the corresponding Stryker's estimate, including endpoint case. Okay, I'll stop it. Thank you for your attention.